So, good afternoon to everyone. So, my name is Luciane Quoos. I am a Brazilian mathematician. I came from Rio de Janeiro. And, well, I'm going to talk about semigroups and the coding theory. How can we make the use of local information on an algebraic curve to improve the parameters, I mean, the minimal distance of an algebraic code? Okay, so today I will talk about function fields. I'll give an introduction on function fields. So, function fields. So let K be a field. Later on, this field will be a finite field. And K bar, it's algebraically closure. Algebraic closure. Okay. Now we look to, you take a polynomial in two variables, let's say f, x, y, with coefficients in k. Oh, and we consider the variety, a affine variety associated to this polynomial. So we look to xf. So these are just the points on the algebraic closure, such that f of a and b is equal to 0. Okay, so, well, so this is the variety associated to f. And we have also the projective variety associated to this polynomial. That is, if the polynomial f, the degree of f is big, then we look to the homogenized polynomial. F is just f in three variables. So now we go to the projective space. So this is just this is the c to the d times f of x over z, y over z. Okay, so this is a polynomial again, because your polynomial has degree d. This is a polynomial in three variables, and this is the homogenized polynomial associated to f. So we have also the projective variety associated to f. So x of f. So these are the points a, b, c in P2, coefficients in k, such that f of a, b, c is equal to 0. Okay, so this polynomial is always a homogeneous polynomial, as you can see. So it makes sense to ask f of a, b, c equal to 0 for this equivalence class in the projective plane. Okay, so this is the affine, let's say, variety of f, and this is the projective variety. So, given so these are the points on your curve. Okay, we are going to need a little bit more things on our algebraic curves. So we are starting talking about the points on the curve. So giving a point P on your curve, A, B, C on F, on XF. Well, if C is different from 0, then this point is just equal to this point, A over C, B over C1. These are the same equivalence class, and to say that this is an affine point on your curve. So this is an affine point on X. Okay, and what if C is equal to 0? Well, if C is equal to 0, so the points of this shape A, B, 0. These are called the points at the infinity of your curve. These are the points at infinite on X. Okay? We also notice that, well, if your polynomial that you start, if you can factor your polynomial f, like f1 times f2, then you can see that the variety associated to f is just the union of the two varieties. Okay? So it's like if you're going to start this curve, you can start this and this. So from now on, we are going to suppose that f is always irreducible polynomial. Okay? So from now on, f is irreducible over the algebraic closure of the field K. Okay? So you cannot factor f as the product of two polynomials of the smaller degree. So we need a little bit more to define an algebraic curve. So at first we have to start with a reducible polynomial, and now we also want a non-singular polynomial. So we say that what is a singular point on your curve? So we say that P on your curve is singular or if you have that f of P, f computed at P0, the derivative on x, fx on P0, the derivative on y is 0, and derivative on zeta of P is 0 also. Okay, so if you remember geometrically, what does it mean to be a singular point? Well, a singular point, it means that if you have your curve, so a singular points are the points where the curve crosses itself. Okay, so the curves we are going to work, this will never happen. Okay, we wanted the non-singular curves. So it's singular if this happened, and well, so if xf has no singular points, we say it's non-singular. Okay. So from now on, we want f to be irreducible over the algebraic closure and also non-singular. So these two conditions. Okay. And well, there is something important associated to x also, to the curve x. That is the genus of the curve. So associated to the curve x, there is an important, well, it's a birational invariant. So there is a number associated to your curve that is the genus G of your curve of x. So, for example, if you have that, well, if f is non-singular of degree D, then the genus of f of the curve is just d minus 1, d minus 2 over 2. Okay, and what it happens if you have singularities on your curve? Well, if your curve, so these are for the smooth curves. So your curve is something like this. And well, if your curve has singularities, okay, so the genus of f is just d minus 1, d minus 2 over 2, and you have to take off a certain positive number. So for each singular point on your curve, you take off a certain number that is the multiplicity of the point on the curve times the multiplicity of the point on the curve minus 1 over 2. Okay, so these are always, well, for singular points, they are always positive. So the nice curves, the genus is just this one. Okay, so we are going to consider from now on, like, so non-singular and irreducible curves. These are the ones that we want. Oh, an algebraic curve, it's irreducible over the algebraic closure, non-singular, and it always has genus G. Curve. So I will start with one example that actually you are going to work with this example during all the curves. So the example, we are going to look to the Hermitian curve. So the Hermitian curve, we look at it over a finite field. So we consider FQ is a finite field of order Q. Q is just the power of a prime, P to the R. So P prime. And the P is P is the characteristic of your field. Okay. So what is the equation of the Hermitian function field? So the equation for the Hermitian function field, you take f of x and y is just y to the q plus 1 minus y to the x minus x. So it's not hard to check that is irreducible, okay? Because, well, if you want a factor, you have just this y to the q plus 1. So if you want two factors, you should have y at certain power in both of them. And, well, you can, this is not too hard to prove that this is irreducible. So this is irreducible. Okay. And what about check if it's singular or not? So we need to do this. So let's just do an example. I'll compute the homogenized polynomial here. So who is this guy? So your curve has degree q plus 1. So this is just z to the q plus 1 times f of x of y. X z and y over z. This is just z to the q plus 1 times y, I put y over z to the q plus 1 minus x over z to the q minus x over z. So what you get is just y to the q plus 1, okay, minus x to the q z, minus x z to the q. So as we can see, we have a homogeneous polynomial. All the each one of these has the same degree q plus 1. Okay, so if we compute the derivatives now on the variables x, y, and z, what we get? So what we get is, what is derivative on x? So you just have on x. So here you have to put q, but q is a power of the characteristic, so this is going to be 0. So you just have this guy. And in a similar way, what's the derivative on y? This is just q plus 1, y to the q. So this is just y to the q. And this derivative on z, on zeta. So here you get 0 because this is a power of the characteristic. And here you get just x to the q. So if you make this equal to 0, this equal to 0, and this equal to 0, the projective point you get should be the 0, 0, 0, but this is not in P2. So this curve is always non-singular. So this is an example, okay, of an algebraic curve. We are going to come back to this curve later on, next class, and in all the classes. So now we are ready to define what is the function field of a curve. So we start again with our polynomial, irreducible. Actually, this you can just say this, it is absolutely irreducible if you want to say this. Huh? Well, so if it's irreducible, then if you look to this ideal generated by F, so this is a prime ideal. And if this is a prime ideal, then what you have? Then the quotient ring over F, this is a domain. So if it's a domain, we can talk about its quotient field. Okay, so this is R. So we have a reducible polynomial, okay, and we look to this ring. This is a domain. So the function field of the curve, the algebraic curve associated to F, is just the quotient field of R. Okay, is the quotient field and our notation for this so we'll write like this. So these are just functions f over g. Okay, so you have that f and g are in R. And, well, g is not 0. Okay. What you are saying is that g is not a multiple of the polynomial f. Okay? So this is your function field. And yeah, there is another way that we can see this. Since you are looking to this quotient, well, when you have your curve, so you are looking to the point that makes f, x, and y equal to 0. Okay? So we can just think, you take the rational function field, so you have x, a variable here, over k, and you add y. Now you think of x and y satisfying f of x and y equal to 0. So actually now x and y are functions. And this has finite degrees. Actually, this is the degree on y of f, since it's irreducible. Okay, so your function field is just k of x and y, where x and y satisfies this relation. So you can also think like this. Okay, and of course you can project your curve on x, but if you want, you can also project on y, for example. So the degree here is a finite degree, and is the degree on x of f. Okay, so if you look here, it's different if you look from here. So you can project in any function you take here. Okay. And well, we talked, everything we said now, we said for a polynomial in two variables. What does it happen if you go to the homogenized polynomial? Okay, what can we say about the function field? Because this is the function field for this polynomial. So let's make a comment here. So for f, the homogenized polynomial of f, okay. So the function field should be k. Now you have the three variables, so it should be k of x, y, and z. This is the function field of the curve with the homogenized polynomial. Well, they seem to be different, yeah? If you look to this one, the projective one, or if you look to the affine one. But actually, as function fields, these guys, they are isomorphic. It doesn't matter if you look to this affine or here. Okay? So it can be shown. It can be shown that this guys is isomorphic to this guy. Okay. Well, and why this? Well, since you can look at P2 over K, but P2 is covered by the union of subsets isomorphic to K2. Okay? Yeah, when you look to who is projective, is this one. So if I make C not zero, I can identify this point with A over C, B over C1. This is the same thing as this. If B is not zero, I can just identify the point with A over B, 1, C over B. And this is just isomorphic to K2 again. Okay, so yeah, what you have is that these are the isomorphic function fields. For example, you can, what you can do these computations. If you take phi index 0 this one, this bijection, AB1. This is a then what you have is that your variety is just the inverse image of the homogenized variety intersection with this guy. So intersection with the points of the type X, Y, Z, such that Z is different from 0. Okay. So you have the varieties isomorphic, so this gives you the function fields isomorphic. Okay, and this is an open set. Okay, in P2. So now I'm gonna change the language, everything to function fields. Okay, we are not going to think anymore just with the polynomial. Yeah? No. Oh. So let X be an algebraic curve. And we are gonna say F, its function field. So this is just K X. Of course, we have a polynomial associated to the curve, but we don't need to write down anymore. So this is its function field. Now, if I give you a point on the curve, given a point on your curve, we can look at this guy. That we are going to call it at first like this, OP. So these are the functions on the function field, such that Z is of the type F over G. You have F and G in R. F. And well, you have fixed the point. You want that G of P is not 0. So G is here, G is not 0 as a function. And we also ask that G of P is different from 0. Okay. So you can show that this is actually a ring, okay? And this is gonna be a local ring. So it has only one maximal idea. It's a longer. And so it's a local ring. Okay, it has only one maximal idea. With the quotient field of this guy is also F. With quotient fields and who is its only maximal idea? We are going to call it P. So it's only is called SP. So who is P? These are the functions F over G, like this. And what we want is that now that F of P is equal to 0. Oh, okay, so it can be shown again that this is this is an ideal, and it's the only maximal ideal. of this ring. Okay, so and P is going to be called a place of your function field. So if I give you a point on your curve, you have associated to your point a place on the function field. Okay, so P is called a place of S. Okay. And well, it happens that P is a maximal ideal and it's also a principal ideal. So P is a principal ideal generated by one guy. We say, for example, so P is of the type T OP. So T is the generator of your ideal in the ring, okay? And we call P is going to be a prime element at the point P. And T is called a prime element at P. Okay, so what is going to happen is if you have a non-singular curve, so algebraic curve, non-singular, given a point, we have a place, and associated to a place, you have the point. Okay, so looking at points on your curve or looking on places on your function field, it's going to be the same thing. So, and now, since this is a maximal ideal of this ring, so we can consider the quotient. So we have the field OP over P. So this is a field, okay? And this field actually always contains the constants, okay? Yeah, you can see from here, no? The constants will be here. Okay, you just make G equal to 1 and F is going to be a constant. So these constants are here. Yes, so you can see the constants inside here. And why this is important? Because we are ready to define what is the degree of a place. So the degree of a place is going to be the degree of this function field extension. Okay? And in particular, if your place has degree 1, it means that the quotient field is just the base field, it's just K. And these guys, like degree 1 places, are the important for us when we are going to do coding theory. So the degree of the place P is just the degree of this extension. So in particular, if the degree of our place is 1, it means that, well, you have this guy equal to K. So, well, now exactly as we know we compute polynomials in points. Now we are going to show we can compute actually functions on your function field on places. We can do that too. How we do that? So given a function z on F, on the function field, we define z of p, by definition, is the class of z at at this field, OP, the quotient field. Okay, so this is just this is just Z plus P on here. Okay. And well, so for each point to have a place, now we can look to the set of all places in your curve. So the set of places in F is this guy. Okay, we have always an infinite number of places, like we have an infinite number of points on an algebraic curve over algebraically closed field. So it's the same here. So we call this. And so for P, for a place in F, we can associate a discrete valuation. And well, how we do that? So we are going to associate a discrete valuation from here. So we are going to put VP from S to zeta union infinite. Okay. So if I give you a function in your function field, so if you look at the place P, it's like you are looking to your function locally. Okay, and locally at your place P, what do you have? You have that P is just a principal ideal generated by T in your ring. So giving a function, what happens is that I can always write the function Z, given Z in F, we can write Z equal to T to the N times U, where N is an integer and and U is an invertible guy at OP. Okay? So, who is T? T is the prime element at the fixed place to have a fixed P. So, you can always do this. Okay? And well, there are some things we are not in, don't have time to see everything, but of course, maybe you don't have just one prime element, you have two prime elements. So you should be able to prove that when you do this N here, it does not depend on the prime element you have fixed in the beginning. And yeah, that's true. Okay, it behaves well if you change the prime element you have fixed at the beginning. So it means that this N here, it's unique. So giving a function Z, what do? You write it locally at the place P like this, and you associate to Z this integer N. Okay, if the function is not zero. And to the zero, you just associate infinite. So this PP is a discrete valuation on F. So what is the definition of being a discrete valuation? in general. So discrete it means because the group you have here is just a discrete group. It's the integer, z. And so we have this. So what we have is that, well, v of z is just is infinite if and only if that is equal to 0. And if you have two functions, what happens with the valuation at P of the product of the functions? Well, you are going to have, you have your function z1 will be like this, z2 will be like this. Okay. So when I multiply both, I'm going to add n1 and n2. Or I can just write this, it's just v of z1 plus v of z2. So we have this. And what else? And this is important, that what can we say about the evaluation at the place P of the sum? Well, this is always larger or equal than the minimum of the vita in Z1, vita and Z2. Okay, this, well, we have a P here. I was like, okay. And so this is always larger than the minimum. And if these values, valuation to Z1 and valuation to Z2, they are different, then you have equality. So we have equality here if we know that these guys are different. Okay? We are going to use this tomorrow. So we have this. And well, since we always have a prime element here, we have something else. Like we notice that there is a function z such that Bp of z is 1. Okay? Because given the place, you look to the, given the point, you have the local ring, so you have this guy that's generated by one guy. This is the guy that gives you 1. So we know this. And also, notice that if you compute the evaluation at a constant, this is going to be 0. Because if I give you a constant will be t to the 0 times a. Okay? So this is just 0. If a is a constant. So now if you just erase all the p's here, this is a definition of a discrete valuation on a field. It has to have these properties. 1, 2, 3 here. Okay, and also 4 if you want discrete. You need one guy that has valuation to be 1. So what we have till now, we have P, a point on X. So we have something like giving a point. We have a place, because it's non-singular, a place on the function field. And now we can associate to a place a discrete valuation on F. So you have bijections between all these elements, points on the curve, places, and the discrete valuations on these fields, the function field of the curve. Okay, and well, so if I give you a discrete valuation, I can recover the ring OP. I can also recover the maximal OP. How we do that? So, given a valuation, VP, or V, a discrete so this guy is just the functions in the function field such that when I compute V on Z, this is larger or equal than 0. So now I just give you the valuation. Okay? And who is P? P is just the function Z such that V of Z is equal to 0. Oh, sorry. This is just the invertible, guys. So this is the unities here. Okay. And the maximal idea, this is just the Z in F such that V of Z is larger than 0. So when you are going to do function fields, you can start to look into discrete valuations on your fields, and then you can prove that this is a ring, local ring, and these are the units in your local ring, and this is its only maximal idea. So you can also go this way. We started from here to there, but you can do from here to here. This is beautiful. So you have this, and so when you have a place, your place actually corresponds a point on your curve. And when you have a point, you can think, oh, is my point a 0, or is it a pole of my function? So giving a place now, we are going to use the discrete evaluation associated to the place to define this. What is to be a 0 or to be a pole of your function? So we say that P is a 0 of F, of a 0 of the function Z in F, if when you compute Vp of Z, this is larger than 0. And you say that P is a pole of the function if this is negative. Okay? So now we have our functions in our function field. They have poles, they have zeros, and you can check this using the evaluation associated to the place. Okay. And now, well, we have all these points on the curve. Now we have a group associated to your points on the curve or your places on your function field. So we are going to talk a little bit about divisors. So what is a divisor? Well, you look to all your places and you take the free abelian group generated by your places. That's it. So the free abelian we use an additive notation, the free abelian group generated by your places on S by PDF is the notation is D, well, like this. So, well, I'm using the notation actually like this is div of F. So, how is an element on div of F? Well, this is going to be an abelian group and additive. So you have things like this. You have sum, where you have places. And here you have an integer. Okay, so NP is just an integer, and P. So you just make sums of NPP, where this guy is an integer, and well, you want that this guy is 0 for almost all P. I mean, you want this to be finite. So NP is in Z, and NP is equal to 0 for almost all P here. So now you can add divisors. How do you add divisors? You just look to the same places in both divisors and you add these guys. So it's simple to add divisors. Since each divisor is a finite sum, when you add, you have again a finite sum of places. So it's okay. And we have these like functions in our function field. They have zeros and poles. So now we can see that given a function, we can associate a divisor. So there is this, like they are called the principal divisors. What is going to be a principal divisor is the divisor of a function. So the principal divisor so we have the, well, so what is, how you define this guy? This is just sum CP of Z, P, and you let P run through all your places in your function fields. Okay. Well, there is something here that we asked that a divisor has to be a finite sum, but yeah, we can show that actually a function, it has a finite number of poles and zeros. Okay, so this is well defined. And if you have the divisor of your function, so you can just look to the zeros. So we can do like this. This is positive. Okay. And we can do this like, well, what's this? And now this is going to be a, oh, plus this is a negative number. Okay. So we can look to the, here you have the zeros, here you have the poles. So this guy, we call it the zero divisor of the function. We denote like this, zero divisor. Okay. And not exactly this guy, but minus this guy. So it should be like, we can put a minus here. So we can just do like this and like this. So this is negative, but minus is going to be positive. Okay, and we have here the, well, I think it's better if I just write down. We have this is the zero divisor of the function, and this is the pole divisor. So here, actually, you have minus the sum of VP of Z P for this negative, okay? So any function, it can be written, the principal divisor of a function, you can think you have the zero divisor plus the pole divisor. And well, remember we had this, like if you have two different functions, Z1 and Z2, you have that the valuation of the product is just the sum of the valuations. So this implies that if you look to the divisor of the product, this is just the divisor of the Z1 plus the divisor of Z2 because of this. And because of the definition of the divisor. Okay? So you always have this. And it's easy also to show that this is an exercise, let's say, the divisor of the inverse of a function is just minus, that the divisor of the inverse is just minus the divisor of Z. Okay, so we have this and this. You know how to compute this. Yeah, no, because if you have your function Z, what was a zero? When you take the inverse, it's going to be a pole. And if you have a pole, when you take the inverse, it's going to be a zero. So, okay, so if I give you a divisor, so given D, a divisor on your function field, okay, so let's say D is like this. So we have the support of D. What is the support of a divisor? Well, the supports are just the places that really appear in your divisor. So the support of your divisor are just the places P such that NP is not zero. Okay, so the guys that you really wrote there. And we also have the degree of a place. So what is the degree? The degree is the sum of NP times the degree of your place P. Okay. Then we had the definition of this guy, degree of P. So this is it. And one thing we should know is that the degree of a principal divisor is always zero. So the degree of a function is always zero. Not the degree of the function. The degree of the divisor of a function is always zero. So the degree of a principal divisor is always zero. It's here. And well, we have also a partial order on this group. I mean, we can compare some divisors. For example, if I have a divisor like this, and you have a second divisor like this, and so you are adding the places. So we say that the divisor A is smaller or equal than B, if and only if AP is smaller than BP for all places. Okay, so this is a partial order. You cannot compare all the divisors. Okay, so if this happens, you say that this divisor is smaller than this one. And now, giving so there is one guy important on your curve that will be the him or her spaces on your curve. Okay, so given a divisor, let's say A, so we have the him or her space, the Riemann, or this space associated to A. So the him or her space will be a vector space over K. So is L of A. So these are the functions on your function field, such that when you look to the divisor of your function, this is larger or equal than minus A. Okay? And you need to add 0 here. So these guys, I'll put like this. So LA is a K vector space. And so what does it mean to a function to live here? What can you say about that? So let's say we have our, this is A. Okay. So we have like this, no? We have the, we want the divisor of the function. So if Z is here, so we have the divisor of Z has to be larger or equal than the sum of the minus APP. Okay, so what does it mean? This means that VP of Z has to be larger or equal than minus AP for any P here. So for example, yeah, if P is not in the support of the divisor A, this guy is 0. So you are saying that VP of Z has to be positive. So you are saying that it has to be a 0, or VP of Z can be 0, or P has to be a 0 of the function. Okay? And what does it happen if this guy is negative? If this guy is negative, you are saying that this guy has to be larger or equal than this guy. So it controls you the zeros. Okay? So saying that it is here, what you have is something like, well, let's do like this, it's better. Huh? We are going to write like sum APP for AP larger than 0, minus so let's do like this. So we already know this is a finite number. Okay. So these guys are positive, these guys are positive. So here you have you want this larger than this. So what you are saying is that your function can have a pole at this guy at most of order mj. So the divisor a, it controls the poles of the function z. So z to be here, you have that, z has zero, has mj, is this one at ei. Okay, because this has to be larger than this. Oh, I did something, because it's minus. So actually, it is minus this. So his has, yeah, okay. Has zeros at these guys, because have the minus a in front of order, okay, of order larger than this. And z has poles as, well, have pole only I think this is no has to be like this. This was okay. And have poles only at these guys, i's of order at most mj. So leaving here, you have actually the poles of the function z more controlled than the zeros. Okay? And well, so this guy is a k-vector space, and we are concerned about the dimension of this vector space. What can we say about it? And so we cannot say too much, but we can say something. If your divisor has large degree, we can say something. But for a small degree, we don't know too much. Let's see. So we call LA, L of A is just the dimension over K of this space. Okay. And we have that the dimension is 0. Well, this is L of 0 is K. Okay? Because constants, they don't have zeros, neither poles. And well, if the degree of A is negative, then you have no one function. Why don't you have a function if the divisor is, well, if the divisor is negative, it's easy to see. Because if it's negative, what happens is that if it's negative, your function should have at least one pole and at least one zero. So if it is negative, you cannot have guys here. So this is just 0. And we also have So I'm going to use all this. So this is kind of a little bit of a review of function fields. If you have A is smaller than B, okay, then you always have that, well, that is to show that this space is contained on this space. Okay. And this is going to be a subvector space. It's just by definition you have this. And then you can say something about this dimension, that the dimension of since it's a vector linear subspace, you can look to the quotient vector space. So this guy has dimension at most degree of the divisor B minus the degree of A. So we also have this. No. And well, these are vector spaces. So what are you saying here? You are saying that if A is smaller than B, this dimension here is just L of A minus L of B has to be smaller than degree of B minus degree of A. Okay? Because this is just the dimension of the quotient. Oh, so now we are ready to define what is the genus of a function field. We have the genus of an algebraic curve that was associated to something geometric. And now when you look to a function field, to define the genus, it will be associated with the divisors on your function field. So the genus of a function field this is another way to see the genus of an algebraic curve. So it's just the maximum of I do degree of A minus the dimension of A plus 1, and I just let A vary on the divisors of F. Okay. So look, if the guy is positive, if you have a positive divisor here, A, okay, this is already positive because of this. So you should have like A larger than 0. So you are going to have that degree of A will be larger than L of A, because this will be 0 and this will be 0. Okay, this will be 1 because it will be L of 0. And this will be 0. So all right, what I just said, notice that if you have this, then you have degree of A is larger, A is larger than 0. So this is larger than L of A minus 1. Which means that degree of A minus L of A plus 1 is larger than 0. Okay? So for positive divisors, this is always positive, and you are take the maximum, so the genus is always larger or equal than 0. Okay, this is very easy to see. And well, do we have a curve with genus 0? Yes, we have. It's going to be the projective line. It means it's the rational function field. So we have, if you look to the rational function field, Fx has genus 0. So what is x? Well, x is a variable over k. So this is the function field of a line, and it has genus 0. And well, what else can we say about the genus? So there is an important theorem that we are going to use in the next classes. It's the Riemann-Roch theorem. So Riemann-Roch theorem. So this will tell you what is the dimension for what is the dimension of a Riemann-Roch space for any divisor. So for that, we need a definition before. Like we say that a divisor W is canonical. Oh, we say that W is a canonical divisor if two things happen. If it has degree equal 2 times genus minus 2, and the dimension of the Riemann-Roch space associated to W is larger or equal than G. Okay? So this is a canonical divisor. And actually, well, the divisor of a differential on your algebraic curve is always a canonical divisor. Okay? So we have this. Yeah, canonical divisors, they always exist. They're not too easy to find them, but yeah. I mean, what do I mean about to find them? If I give you the explicit equation of a curve, how can you find a divisor with this property? Oh, because if you want to do coding theory, we have many like explicitly computations. So you need to be able to really to compute things. Okay, compute canonical divisors, compute functions to find the functions with a certain number of zeros or poles, these kind of things. So Riemann-Roch theorem, now we are ready to write it down. Oh, for this guy, you have that the dimension of the Riemann-Roch space is just the degree of A, degree of the divisor, plus 1 minus G, plus the dimension of W minus A, where W was the canonical divisor. Okay? And G is the genus. So, what happened? What we saw before is that if you have a divisor of a negative degree, then the dimension of the Himmelhauer space associated to it is just 0. Okay, so for example, if this guy has degree negative, then I know that this is going to be 0, has dimension 0, and then we have that the dimension of the Himmelhauer space is just degree of A plus 1 minus G, so I can compute it. So this is a simple case. So if degree of W minus A is negative, what does it mean? It means that degree of A is larger than degree of W. W was a canonical divisor, so W has degree 2G minus 2. So if your divisor has large degree, well, this is negative. We know that the Himmelhauer space associated to it is 0, so this disappears. What we have is that the dimension of A is just the degree of A plus 1 minus G. Okay. So we know things like for degree negative from here, we have just 0. For degree larger than 2G minus 2. So here we can compute. Okay, and well, the problem is here. What is this dimension? So you have well, digamos, a small place where you cannot compute usually the dimensions. Okay, so people investigate these cases too. Okay. So now we are ready to show the Weierstrass gap theorem. And the Weierstrass gap theorem is going to lead us to the definition of Weierstrass semigroup. So we are going to have the definition of semigroup today. Well, the course was semigroups and the coding theory. So we are going to define semigroups in 1 point today. And next class we go for 2 points and well, the relation between them. So let's do this. Just so we start with a place of degree 1. Okay, so, and I just want to, well, I want to introduce a notation also. A place of degree 1 for us, it will be called a K-rational place. Okay, okay, place of degree 1. And then, and you consider this. Then we have this, huh? We have that the divisor, let's put like 0 is smaller than this, and this, and they can just go on. Okay? And we have seen that if I have a divisor smaller than other one, then we have the Riemann spaces, they are contained also. So we have this, we can go and look to the Riemann space, this is contained on this. They could be equal, huh? We don't know. I can just go infinitely here. So our question is, what happens to the dimension of these Riemann spaces? So we just saw something, no? We saw like if the degree of, we have this guy, 2G. 2G minus 1. So what we want to know is, what can we say about the dimensions? So we saw this is just the field K. So this one has dimension 1. Okay. Here, the dimension could be 1 or 2. We don't know. But we also know something. We know that if n, we just saw this, if n is larger than 2G minus 2, then the dimension of Ln of P is just the degree of NP plus 1 minus G, and there is nothing else, because here we should have the dimension of a zero divisor. Not a zero divisor, no, of a negative divisor. Okay? So P was rational, so the degree of this guy is just n. So this is just n plus 1 minus G. So what we are saying is that from 2G minus 2 from here to there, so what is the dimension here? If I make n equal to 2G minus 1, we have that L of 2G minus 1 is just 2G minus 1 plus 1 minus G. This is just G. So this guy has dimension G. Okay? And what is the dimension here? Well, by this, the dimension is just n plus 1 minus G. So if you increase n by 1, you just increase the dimension by 1. So dimension here should be G plus 1, G plus 2, and so on. So what happens is, you have dimension 1 here, you have dimension G here, and you have how many jumps from here to there? You have 1 jump, 2 jumps, you have 2G jumps. So what happens is you should have equality here, G times, and inequality G times, in such a way that this goes correct. Okay? So there are G was the genus, there are G values S between, well, 0, 1, 2G minus 1, such that you have equality here. Or you have inequality. So, such that L of I want to put like this. So I should take off this guy. Yes. Because I have -1 here. Yeah. So we have G times, we have equality and we have inequality. What does it mean when you have inequality? Well, we have that this space is contained here. So if they are not equal, what happens is that, well, there is a function z that is here and is not here. Okay, this is just by definition. And what does it mean the function lives here? Well, it means that the divisor of your functions is larger or equal than minus SP. Oh, well, this is a function. It has to have at least one pole and one zero. So if this is happening, this function z has to have a pole on P of order at least minus S. At least, no, at most S. So this tells you that the function z has a pole only at P. And it has to have a pole there because a function that is not a constant has to have a pole. Okay? And what does it mean that zeta is not here? Well, it means that the divisor of zeta cannot be, well, now it's cannot be bigger than this guy. So what we have here, it should have a pole at most of this order. And the order cannot be s-1, because if the order of the pole was s-1, then the function would be here. So the function zeta has to have a pole of order s exactly at P. So these two things together tells you that the divisor of pole of function z has to be this guy. Okay, it has to have a pole only at this guy, at most of this order, and it cannot have this order. So it has to be this one. So so from this we have the definition. We say that F is a gap at P if you have equality of these dimensions. Okay? So why do you use the word gap? Well, use the word gap because it misses the function. So it's a gap when you have equality. You don't have the function. And you say that S is a non-gap if you have inequality here at P. So given a place of degree 1, we have associated to it G gaps and the G non-gaps. Okay? So given P of degree 1, we have G gaps, G gaps, S, that means it's a gap if this happens. And we have G non-gaps. So non-gap, to be a non-gap, there is the function. So you have this contained but different. Okay. Well, G is the genus, okay? So and well, this is the Weierstrass gap theorem that given a place of degree 1, you have like G gaps, or you can also say that you have G non-gaps. So let's take a look now to the set of non-gaps. What's going to happen if you have a non-gap? So our notation is going to be is this one, HP is S such that S is a non-gap. So note we have already proved something. Huh? We have proved that if S is larger or equal than 2G minus 2, then S is always here. Okay? Because we saw that the dimension is always growing 1 by 1. So now we have this, and okay, for okay. And what else can we say? There is something important also. If you take two guys here, S1 and S2, so you have two non-gaps. So what does it mean by definition? To be a non-gap means that there is the function. So for S1, you have a function zeta1 with a pole divisor equal to S1p. So if you have these two functions, you have that there is these two functions, zeta1, zeta2 in F, such that the pole divisor of zeta1 is just S1p, and the pole divisor of zeta2 is S2p. But then, if you look to the pole divisor of the product, remember we just saw that the principal divisor of the product was just the sum of the two principal divisors. So this is just, this will be just this one plus this one. And this is S1p plus S2p. That is just S1 plus S2p. Okay? So we conclude. What can we conclude? Well, if I give you two non-gaps, you just found a function zeta1, zeta2, such that the pole divisor is exactly S1 plus S2. Well, this means that S1 plus S2 is also a non-gap. So we concluded that S1 plus S2 is here. Okay. And we always have that 0 is a non-gap. Yeah, because you have like yeah, 0 is okay. 0 is a non-gap because you have like this, no? You have 0, and here you should have L of minus 1p. This is k, and this is 0. So this has dimension 1, this one has dimension 0. Okay? So here we have that this set is closed by addition, and we also have that 0 is a non-gap. So we have that 0 is here, and this guy is closed by addition. Well, and this is considering natural numbers. So, yeah, a subset of the natural numbers with this property that 0 is on it and is closed by addition, this is called a semigroup. So HP is just a semigroup, and actually this is the Weierstrass semigroup at the point P. So HP is the Weierstrass, is a homage to Weierstrass, Weierstrass semigroup at, well, at the rational place P. Okay. And so this is the Weierstrass semigroup, and we also had the gaps. So what are the gaps? The gaps is just the complementary in the natural numbers. So GP is going to be the gaps at P. This is just by definition N minus the Weierstrass semigroup at P, and it has cardinality G, as we saw. So, of course, you have infinite numbers of non-gaps and exactly G gaps. This is the Weierstrass theorem, we just saw it. Okay? So, what we want to do is, we want to connect Weierstrass semigroup non-gaps with coding theory. Okay? So, what we'll do tomorrow, we have defined Weierstrass semigroup for 1 point. You can do this for more points. So we are going to have like 2 points, rational points, and we will define what is this. The Weierstrass semigroup in 2 points, subset now here. Okay. And well, how can we compute this guy? So can you compute this guy? So we are going to prove that's kind of a very nice result that you can connect, well, this guy that I haven't defined yet, but with the gaps at P and the gaps at Q. You have a connection. If you know this set and you know this set, in a certain way, you know this set. Okay, so we are going to prove how can we recover this from these guys tomorrow. And well, we are going to give an example how to compute this on the emission function full field that we have just presented today. So we'll come back to this tomorrow. Okay, so well, this is all for today. Thank you all for coming and watching this class.